All right, so now we're going to talk about epoxides. If you think about a cyclic ether, we can have a cyclic ether with any number of carbons, right? So the most interesting one, the one that we're going to talk about, is a three-membered ring, right? So two carbons and an oxygen. I guess these are called oxyranes. There actually are common names of epoxides that have this oxyrane ending. We're not gonna worry about that. But FYI, and an oxyrane is more commonly known as an epoxide, right? So an epoxide is a cyclic ether with three members in that ring. You can have up to four substituents. One thing about the epoxides is they're almost always going to be stereocenters. Unless these two groups are identical, you will have these stereocenters. Okay, so that's just something that we're going to have to keep in mind. Of course, there are epoxides in nature. Turns out that epoxides are relatively reactive. So they're good sort of intermediates for reaction pathways. And so we're going to talk about a bunch of reactions for epoxides. First, we're going to introduce them, learn how to name them. They have their common names. So for example, the simplest one is ethylene oxide. We're going to learn the systematic naming scheme, the IUPAC, and that's all I'm going to test you guys on. Okay, so the IUPAC system for naming epoxides, similar to before, you're going to find your parent chain, the longest number of contiguous carbons that includes those two carbons that are bound to that oxygen, right? So the epoxide ring, the two carbons in that epoxide ring should be located within the parent chain. So before we get onto this complicated one, let's just look at the simplest one here. And then you number your parent chain 1, 2. And then you actually refer to the position of the epoxide group with both of those carbon numbers. So this would be 1, 2, epoxy ethane, right? It's a 2-carbon parent chain, so that's why it's an ethane. My epoxy groups are located on carbons 1. This drove me nuts for a while because epoxides by definition are always 2 carbons apart. So why can't I just refer to it as, one epoxy, much like we do with an alkene? It turns out that the answer is you can have these quite complicated epoxides where there's a ring and there's this bridge on this ring that's the epoxide. And so we're not going to get to examples where they're not right next to each other, the carbons that the epoxide's bound to, but they do exist. So that's why we have to indicate the position of both of those carbons. Okay, so now let's go on to our more complicated example here. Again, I'm going to find my longest set of contiguous carbons that contain that epoxide functional group. I'm going to number in such a way that gives that epoxide functional group the lowest number possible. So 1, 2, 3, 4, 5. And then I'm going to list all my substituents in alphabetical order, keeping the epoxy for last. So that one doesn't go in alphabetical order. It always goes just at the very beginning of that parent chain. So in this case, I have an ethyl group on carbon 3. Let's just color code here. That's where this one gets its name. I have this methyl group on carbon 2, and then I have my 2,3 epoxy, and my parent chain is 5 carbons long, making it a pentane. Okay, but notice that epoxy is not put in alphabetical order. It's not over there between methyl or ethyl and methyl. It always goes at the very beginning of the parent chain. Okay, and then again, it's quite often that we create stereocenters with our epoxides, right? So in this case here, I would have 2 stereocenters. Assigning stereochemistry is the same as always, but let's just practice because things might look a little bit different now that we're trapped in this really weird ring. Again, I'm going to go to each carbon, so let's just color code. I'll make this one my orange carbon, and I'm going to number priorities. My oxygen is going to get priority 1. That's the highest molecular weight. Now I have these two carbons here, and I have to determine which one's going to be higher priority. Notice because this one is bound to that oxygen, it's very often going to get priority 2. And then lastly, that methyl group would be priority 3. Priority 4 is this hydrogen that's pointed back. Because my lowest priority group is pointed into the page, that means that my rules are normal and counterclockwise would be S. So this orange stereocenter is going to be S. Now I'm going to go choose a different color. Now we got to assign this stereocenter here. Again, my oxygen gets 1, the highest molecular weight. It's not weight, sorry. I know I always say that. Highest atomic number. They do correlate, but it's atomic number that matters. This carbon will get priority 2. So this carbon is priority 3. And then the hydrogen that's now pointed at me, I guess I can draw that a little bit less deceptively, pointed out at me, is going to be priority 4. Remember that the rules reverse when the lowest priority group is pointed at you. So now, even though I'm going clockwise, the rules are reversed, and so clockwise would be S. So this is again an S stereocenter. So the full name for this molecule here, again, I got to find my parent chain. That's 1, 2, 3, 4, 5. So it's 2S, 3S, 2, 3, epoxy, pentane. Okay.